We are going on time. We still have a few seconds. So for people who just arrived at Berkeley, they have this rule. Everything starts at least 10 minutes after the hour. Unbelievable. Nobody shows up before 10 minutes after the time they're supposed to start.
Except for the San Jose.
Except for yeah, we are in an oasis here. We are in an island.
So what happens when people show up 10 minutes late to the 10 minutes after?
They do. That's your process. Okay, so welcome everyone to the afternoon session. We have two talks on constraint satisfaction. The first will be given by Kuldeep Meel.
Thank you. Good afternoon, everyone. So first, thanks to the organizers for inviting. I'm going to talk about our work. This is joint work with Arnab Bhattacharya, who is a faculty member at NUS Singapore, Pawan Aduri, who is an audience faculty member at Iowa State, and N.V. Vinod Chandran, who is at University of Nebraska. So I guess it's kind of the theme of the day. We had no relationship to the world of Semirings, and then Val was spending sabbatical at in Singapore, and also Vinod was there for sabbatical, and then Val got us into the world of Semirings. So he introduced us to this problem. I'm going to talk about what we have, and at least to us, it looks like there are lots of interesting questions to pursue. Okay, so I kind of come from the world of satisfiability, Boolean satisfiability. So in this world, you have a formula, and the kind of question is there a truth assignment to the variables so that the formula evaluates to true? In this case, as you can see, there's no such truth assignment. And then Well said, you know what, you should look at through the world of semiring. So there's a semiring, there's an interpretation for the operators. And now you can ask that the same question can be formulated as compute the maximum value over all interpretations. And as you can see, a formula is satisfiable if and only if the maximum value evaluates to 1. Okay. So now we start asking, well, what happens beyond Boolean interpretations? So maybe if you look at Viterbi semiring interpretation, this is kind of very nice in sense, and our Boolean is also multiplier, or our Boolean is also max. So the only thing that changes is the domain. So the domain now is 0, 1. And we had to talk about negation. So let's say we are focused on negation as 1 minus x. I'll come back to this to comment a little bit. And now the question we can ask is, well, compute the maximum value over all interpretations. For the formula that we have here, the maximum is over this polynomial. Both of them turn out to be symmetric, so we can just focus on one of these. And the maximum value that turns out here is 0.25. So a formula that is unsatisfiable can have a value somewhere between 0 and 1. You can see I only have 10 slides, so if there are any questions, please ask there. And the thing that I want to talk about here is that there are some very, very cool and simple things you can do. So how to maximize this? You can say you can take this expression x2 into 1 minus x2 takes value at, or x1 into 1 minus x1 takes value at 0.5. Yeah.
I'm going to ask the same question as the morning. So maximum with respect to what order?
So we are considering the natural order. Let's say, yeah. Right. So some simple observation. The formula is satisfiable if and only if the maximum value is 1. Here we are going to consider the formula in the negation normal form. In particular, here I have written what is called conjunctive normal form. So if it is satisfiable, then the value you can evaluate to 1. Okay.
Just to make sure a naive observation, you apply distributivity here to get to that expression. Am I correct?
Yeah. Yeah. Exactly. There is always as we chatted more with Well, the negation turns out to be bit of Achilles heel in this area. So what we are looking at is one interpretation of negation, which is 1 minus x in case of Viterbi, and similar interpretation for other semirings. The results I'll talk about in particular, I'll show upper and lower bounds. Any kind of reasonable interpretation works out. So all we need is negation of negations should be same, and then negation of 0 to be 1, and so on.
Do you define minus? How do you define minus?
Yeah, so minus in this, it will depend on, this is really just looking at the, all we want is the 0 element. So the one element to define, I mean, for every semiring, it is kind of very easy to see what we are looking at it. Okay, so this is just the additive inverse that you are looking at. Yeah. So the semirings that we looked at are, the Viterbi semiring. There is motivation for it coming from database provenance, as we looked at. There's also work in the world of CSPs. There was a lot of work, and also from hidden Markov models, tropical semiring, fuzzy semiring, access control semiring. So our results apply to all these different semirings. So the problem that we looked at is that you have given a semiring and a formula, which is in negation normal form. The problem of interest is compute the maximum value. And the question we are looking at is, what is the complexity of this problem? Okay. It turns out there was a long history of work that in the CSP community that tried to develop techniques for it. But surprisingly, we didn't find any work on computational complexity perspective for cases other than Boolean semiring. So all these questions, very natural questions, somehow turned out to be studied. And our result is that in case of fuzzy and access control, the complexity is same as the Boolean case, so it can be reduced to the Boolean case. In case of Viterbi and tropical, because those are isomorphic to each other, the complexity of this problem lies between FP. So this is a polynomial time Turing machine that can make calls to NP oracle. In particular, if you allow logarithmically many calls to NP oracle. So this is hard for the FP to NP, the log calls. And it lies in the class polynomially many calls to NP oracle.
So, you know that the opal is this NP log hard? That's the...
Yeah, so we are going to, I'll talk about both the sides. And I think I hope you will enjoy for next 15 minutes. The proof arguments are also very simple and beautiful. So let me get you through those arguments. Are the results clear? So it is hard for FP to logarithmically many calls to NP oracle. It's contained in polynomially many calls to NP oracle.
I'm still confused about the minus for the various semirings. You showed us like 4 semirings on the previous slide.
Yeah.
But it's not obvious what the minus operator should be for each of them.
So maybe I can come back to it later. So it's really looking at the top and defining the minus value from the top. But of course, for access control, we have to define. Yeah.
Do you need a total order?
Yeah. So we are assuming the natural order. Yeah. In case of Viterbi, it's just between 0 and 1.
Can I guess the intuition of the minus for the tropical semiring? So you map infinite to 0 and 1 to 1.
Yeah.
Does it matter how you map everything between 0 and infinite to each other? Because it's not so like minus, not obvious. I think that's the question. Like 1 over?
Yeah.
Oh, say 1 over.
Yeah.
About the connection to CSP, we cannot see this problem as mapping to a structure with
Sorry?
If we think about the connection to CSP, can we see this as I had my formula that I want to take a satisfiability of, which is a structure?
Yeah.
It has a homomorphism into something that would be dependent on the semiring.
I haven't thought about that. I mean, I'm kind of generally thinking you have a formula and the domain elements take value between 0 and 1. But less. Okay, so let me show you how we can, there are two results here. One is how do we show the upper bound, that you can solve the problem by making polynomially many calls to NP oracle. And simple idea would be that we should do a binary search because the values are between 0 and 1. So you try to do a binary search by making multiple calls, that is the optimum value greater than some value v. The issue here is that you can take all the real values. So how do we know where to stop? So since the value can be any real number, so we don't know how to stop. And it's also not hard to see that it can really take infinitely many values a given expression. So here is how it works out. So let's go back to the simple formula we considered. And let's try to think about what's the optimal. There is some optimal interpretation. And suppose I told you, I'm going to focus right now on the CNF when things are represented in a conjunctive normal form, but everything generalizes to negation normal form because you can work over proof trees. Okay. So in case of CNF, suppose I told you that from each of the clauses, the literal that takes the maximum value, right? So for example, let's say I promise you that in the optimal interpretation, in this clause, the literal that takes the maximum value is not x2. If you know it, then we know that the pi hat of f is pi hat of x1 times pi hat of x2 times pi hat of not x2. Then we can rewrite in this expression here. Okay? The next step is going to be, well, if we know this is the expression, then we can maximize this for both pi hat of x1 and pi hat of x2, and those maximum values are 1 and 0.5. So we can generalize this idea. Let's just again focus on the CNF. If you knew that xi takes the maximum value in, let's say, li clauses, and not xi takes the maximum value in ki clauses, then what would the value pi hat of f look like? It will look like pi hat of xi to the power li times 1 minus pi hat of xi to the power ki. And it will be product of all of them.
So, I'm still behind. So in the second bullet point, the property you used here is the selectivity property of the semiring addition, the max, right? So Mr. Wittenberg says you choose one of them, which is the max, because of the max. So that allows you to do this binary search.
Yes.
So the selectivity property allows you.
No, right now, the way to understand is, suppose I told you from each of the clauses, which of the literals contribute to the maximum. Then what would the formula evaluate to? It will be really, you have the end, so it's product of the interpretation for every clause. And for every clause, I tell you which, what the maximum evaluates to. So it evaluates to one of the literals, right?
Yeah, but only because you have a selectivity property. The max of 0.8 and 0.9 is 0.9. If it's multiplication, then it doesn't work. So the selectivity, this means the operator plus is always one of the two inputs.
Yeah.
Yeah. Allows you to do this.
Yeah. Absolutely. All right. So in that case, we can maximize this expression. Well, I mean, what is this expression? This is really xi to the power li 1 minus to the power ki. So the maximum value turns out to be following. So if I know that from each of the clauses, which of the literals take the maximum value, I can compute the maximum value just by knowing that information. And now we know that the maximum possible values are always going to be of the following form. And this turns out to be, again, well-studied sequence of number. These are Farey sequences. So there are only exponentially many maximum possible values. So we can do a binary search over the space of all these exponentially many possible values. So the key observation is that while the formula can take infinitely many, it can take any real value. So, but the maximums can only be exponentially many. So you can do a search, binary search over those maximum values. Now just doing a binary search kind of works out. Okay, so what about it being hard? So can we show some hardness? And in this case, it turns out that we can show that it is as hard as max set. Why so? So the key technical lemma that allows us to prove this is if given a formula in CNF, and then again, things again generalized to the negation normal form. If we have a CNF formula with m clauses and it has R is the maximum number of satisfiable clauses, then the maximum value the formula can take in the Viterbi semiring is 1/4 to the m minus r. The proof is again relying on that maximum values are of this form and then working out a little bit about Li's and Ki's. Right, so, well, here is kind of again a very simple reduction that should work out. We take a formula f, we are going to reduce, the reduction works about by taking a formula f, we will construct another f prime, where essentially every clause of Ci we replace by Ci or Yi and not Yi. Okay, so we double the number of clauses. And we introduce new fresh variables Yi's. Now I would like to claim that the optimal value for f prime is really 1/4 to the m minus r. Why so? Well, I can actually give a very simple interpretation so that this optimum is achieved. What's that interpretation? Look at the max set assignment. So either all the clauses that get satisfied, we don't have to worry about, just take the max set assignment. And for the clauses that are not satisfied, their Yi takes value half. And there are exactly m minus r clauses that are not satisfied. So the value we take is 1/4 to the m minus r. But we also know from this lemma that, well, this is the best possible because the total number of clauses in f prime is 2m. And the maximum number of clauses that we can satisfy here is m plus r. So 2m minus m plus r is m minus r. So this is indeed the maximum value. So if we can solve optimum value over semirings, from here I can deduce the max set value.
Can you maybe repeat the argument for the confidence bounding lemma? Why is the value of f upper bounded by that quantity?
Yeah, so I'm going to give you almost the full argument. So I'll lie a little bit, but if you don't catch me, you will like it. So the optimal values are anyway of the following form.
Why is that?
Oh, that comes from the previous.
Well, I personally didn't understand this either.
Oh,
So the LIs, they are not independent. You have, for each clause, you have xix, jxk.
yeah,
Only one of them will be the maximum.
yeah.
So the numbers Li, L1, L2, L3, they are not independent. There are some constraints. So I don't
Yeah, but
understand this.
whatever those constraints are, once you see that pi head of xi and pi head of xj are independent, so the maximum value pi head of xi will take. What will maximize pi head of f when you set pi head of xi to be Li over Li plus ki?
Why do you say pi? I understand the first equality.
Which one? This one?
Yeah, this one is clear to me.
Okay, now
But
let's see.
what about the second one?
Well, given this expression, for different xi, they are all independent. I mean, pi head of all the xi's is independent of each other. And what about this expression? What will be the value that will maximize the following expression? The value that will maximize the following expression is really Li over Li plus ki.
Okay, and you're saying if you maximize this one, you cannot break the assumption that this is a maximum value.
Yeah, because if there was, then you would get something else.
I don't know, but I'm happy. So if
Okay.
You are the chair, so okay, so this is the expression you get, and in this case it turns out, I mean, it takes the maximum value when both Li and Ki are same. The expression gets maximized over that, and from there we had to labor through a little bit to say that this is 1/4 to the m minus r. Okay. And then the rest of the thing follows. Okay, so where do we go from here? Well, there are two things. There are two results we have. One, that max set can be reduced to opt well. So I have some very speculative thoughts. The thing that I find interesting is that somehow, usually, if you relax a problem from only taking discrete values to continuous values, it becomes easier, but that's not the case here. So maybe trying to solve this continuous problem might be a way to solve some discrete problems. There are lots of continuous methods being developed because the opt-val is really product of max, which is sum of the log of max. So maybe there is a better way to solve max set problem by focusing on the opt-val, and from there you can generate the max set solution. There is some work in the field of neural networks that have been trying to look at these kind of logic tensor networks and so on. So it might be interesting. I mentioned to some of them, they are trying to look into it. So, and I have some more concrete thoughts, which are about that the problem is between FP to NP log and FP to NP. There is a gap here. Can we try to close this gap? If we try to get you interested that trying to close the gap either way is going to be really cool. Maybe the problem lies in FP to NP log. Well, then we know that if we manage to prove it, then there is a lot of work in max set solving. We can use those max set solvers to solve the problems or the semirings, and which will be nice because other problems anyway reduce to set. So all of these constraint problems can rely on the progress in set and max set. The max set solvers don't typically do a binary search. There are very sophisticated techniques that have been developed in the field of set and max set solving. So we'll be able to rely on that progress to solve the problem here. And of course, then there are lots of questions. How do you encode to max set? And also, can there be specialized algorithm that can outperform max set best set process? Maybe it's hard for FP to NP. In that case, one, there is a very natural problem that's complete for this class, because this class is a bit frustrating. Kind of the only problem that we know are complete are Lex, Max set, but even if you try to convince someone that's a problem interesting, it's usually hard to convince. But this is much more natural problem to look at. So if we can show that this is, if it lies in FP to NP, then how do we design practical algorithms that can rely on progress in set solving? But as I mentioned that even for max set, you don't call these solvers in a black box manner. There are much more interesting techniques that have been developed over the years. So I think trying to close the gap either way would be interesting. We have tried for a while and we don't know how to go about it. So I would like to invite all of you to join this adventure. So with that, I'll conclude. I'll be happy to take any questions.
We do have time for questions. Yes, sir, Pierre.
Just there is a related problem, which is about you take a valuation and you look at the value, but by only the positive literals, you multiply them. And then you try to look at the maximal value. And this, we know this is max at. So it's not exactly the definition you have. But
yeah, definitely. I think.
But there are some related programs that we can translate, at least. We think that we can, there is no mistake. We think that we can translate to them.
Yeah, I think that would be. So you only look at the positive.
No, in general, we can even, I don't remember exactly the construction now, so that's why I went to the positive one, because I'm sure about it.
Okay.
But typically, normally, in the definition that we had, we could put different values for the positive and negative one. Okay. But typically, we just say, oh, I put a value for the negative literal and another value for the positive literal.
So I'm trying to recover the assumptions that you made on the semiring. So the results you showed us is they work for the Viterbi semiring.
Yeah.
Right. So one assumption is that you want the plus operator to be really max.
I mean, because for access control and others, we have other results that I did not go into. They're just reduced to the Boolean case, so they are NP complete.
Okay, but so one of your construction was that in each clause you decide which literal is a maximum.
Yeah.
Now, if I interpret the clauses as a sum in the semiring, it means that the sum must be equal to one of the elements I'm adding up.
Yeah.
I think Wolfgang gave a name to this.
Yes. Selectivity.
Selective. The operator.
Yeah.
So this is definitely one assumption that you have made here implicitly. But you also made some assumption about the minus, and I'm trying to wrap my head around this. The negation, you interpret it as 1 minus pi.
Well, yeah. So you could look at it. It can be, it doesn't have to be 1 minus. It will be okay even if it's C minus some value, but
it boils down to the formula that you wrote here. In order to maximize that quantity, the product, you need to know something about the minus.
Yes. So essentially, exactly. So maybe that will be all we want is figure out how do we compute the maximum value of this expression. Right. Pi hat of xi times pi hat of not xi. So if there is a way to compute the maximum, everything is okay. Yeah. So 1 minus allows you, but so in the paper we talk about continuous, like you should take the values so that you can compute the maximum. We need something to make progress from here. Yeah.
So those slides go a long way, but we still have time for one more question. Yeah. Okay, then let's thank the speaker.
Thanks.